Floating point operations are crucial in programming, especially when dealing with real numbers and requiring a high degree of precision. In Zig, floating point operations are designed to be both efficient and predictable, with a feature that enables developers to switch between strict and optimized modes depending on their needs. So far, we learned about the exciting programming language Zig, focusing on its straightforward approach to operators. We explored various operators, including arithmetic, bitwise, and logical operators, highlighting their predictable behaviors and efficient usage in code. Understanding these operators enhances our coding practices and promotes clarity in programming. Zig's emphasis on simplicity aids developers in writing elegant and efficient code without the complications of operator overloading. Now we will talk about advanced floating point operations in Zig and how to utilize strict and optimized modes effectively. Now let's see how we can implement a straightforward addition of two floating point numbers in Zig. The code begins by importing the standard library, which provides useful functions for debugging and other operations. In the main function, we declare two constants, x and y, both of type F64, which is a double precision floating point type. We assign 1 to x and 2 to y. The operation we are interested in is the addition of these two values. By declaring another constant result, we store the sum of x and y. Lastly, we utilize the std debug print function to output the result of the addition, demonstrating how Zig's strict mode governs these operations, ensuring that we obtain the expected output of 3. This simple code effectively showcases how Zig handles floating point arithmetic while following the IEEE 754 standard, thereby highlighting the importance of precision and predictability in calculations. Now let's see how we can utilize Zig's optimized mode for executing floating point operations efficiently. In this example, we define a function called optimized operations. Inside this function, we declare two floating point constants, x as a large number 1e10 and y as a very small number 1e10. We employ an inline loop that executes twice, where each iteration performs different computations. The first iteration adds x and y, while the second subtracts y from x. By handling the operations in optimized mode, Zig is configured to enable faster execution of these calculations, which is particularly advantageous in performance-critical applications such as graphics rendering or real-time physics simulations. To observe the results, we use std debug print, which will output the results of our calculations, indicating which block was executed and displaying the resulting value. This approach highlights how switching to optimized mode can not only enhance speed but also streamline feedback during testing, particularly when handling large datasets or complex numerical calculations. Finally, in the main function, we call optimized operations, invoking our defined computations and showcasing the efficacy of optimized floating point arithmetic in Zig. Now let's take a look at how floating point precision can be tested through a simple multiplication operation in Zig. In this example, we define two constants, small set to a very small value of 1e10 and large set to a very large value of 1e10. By multiplying these two numbers, we aim to observe how floating point arithmetic handles this scenario. Here, the result of the multiplication is assigned to the product variable, which could lead to potential precision issues. When printed, this result might yield 1 instead of the anticipated output of 1e0. This discrepancy occurs due to the limitations of floating point representation in handling extreme values, illustrating the critical importance of understanding precision in calculations. By running this code, you will see firsthand how Zig's default strict mode helps to catch such precision-related issues. It's particularly insightful, as the behavior highlighted here emphasizes the necessity to consider floating point representations carefully, especially in applications where accuracy is paramount. Understanding these challenges will guide you in structuring your calculations more effectively as your needs evolve. Now let's see how we can handle division by zero in Zig, which demonstrates the language's robust handling of special floating point values. In the following code, we define two variables, a and b, where a is set to 1 and b to 0, 0. The crux of this demonstration lies in the division operation where we divide a by b. It's important to note that this calculation would normally lead to a division by zero, a common source of runtime errors in many programming languages. However, Zig gracefully handles this situation by returning positive infinity in accordance with the IEEE 754 floating point standard. The output is printed to the console, providing clear feedback of the operation's result. This behavior ensures that the program does not crash and instead continues executing, which is crucial for applications where stability is paramount. By leveraging Zig's capabilities in managing such scenarios, developers can create algorithms that can confidently handle unexpected inputs or calculations without compromising reliability or performance. This feature is vital in scientific computations and other critical applications where precision and consistency are essential. Now let's take a look at how we can examine the precision of floating point operations in Zig through incremental increases. We will write a simple program that starts from 0 and adds a very small value, specifically 1e10, in a loop running 100 times. In this example, we define a variable number initialized to 0, 0, and each iteration of the loop increments number by the increment value. As we execute the loop, we print the current index and the resulting value of number after each addition. By doing this, we can observe how the results evolve as we continue to add a small increment to a larger value. It's critical to recognize that, due to the limitations of floating point precision, the output may diverge from our expectations as number grows. This exercise reinforces the necessity of being aware of precision issues that can affect calculations in real-world applications and encourages students to code with a discerning perspective towards floating point arithmetic. Understanding such nuances is essential to ensure accuracy and reliability in software development. Now let's take a look at how to perform rounding operations on floating point values in Zig. In this specific code snippet, we begin by importing the standard library, allowing us to utilize various functions and features provided by Zig. We define a floating point variable called value, initialized to 2.7. Using the std_math round function, we round this value to the nearest integer, assigning the rounded result to rounded value. Next, we use std_debug_print to output the value of rounded value. When we run this code, it demonstrates the rounding functionality effectively, producing the output rounded value 3, 0. This showcases how Zig's math capabilities can enhance your application by controlling the precision of floating point calculations. Furthermore, rounding operations are integral when dealing with real numbers, as they can dictate how results are interpreted and manipulated within the context of your application. This flexibility allows developers to tailor their mathematical operations based on specific needs, leveraging the robustness of Zig's features for improved numerical handling. Now let's take a look at a practical example of comparing floating point numbers in Zig, which is crucial due to the inherent precision issues that arise in floating point arithmetic. We begin by defining a function called r=, which takes two floating point numbers and a small margin known as epsilon. This epsilon serves as a threshold for determining whether the two numbers can be considered equal. The function calculates the absolute difference between the two numbers and checks if this difference is less than epsilon, thereby allowing us to account for minor discrepancies that often occur in floating point calculations. Next, we implement the main function, where we define two floating point numbers, a and b, that are very close in value along with a defined epsilon. By utilizing the r= function, we can effectively compare these two values. Depending on the outcome of this comparison, the program will either print a message indicating that the values are considered equal, or it will state that they are not equal. This comparison approach is essential for developers to ensure that their floating point operations remain reliable, even when dealing with very small differences. In conclusion, understanding advanced floating point operations in Zig allows developers to handle real numbers with confidence and control. From determining when to use strict versus optimized mode, to recognizing the challenges posed by precision, zeros, and special values, Zig empowers you with the tools necessary for ensuring the integrity of your calculations within your applications. Embracing the nuances of floating point arithmetic will not only enhance your coding practice, but also solidify your application's reliability and efficiency. So next time you encounter floating point math, remember that Zig's got your back, whether you're rigorously adhering to standards in strict mode or speeding through your calculations in optimized mode. Happy coding, and keep exploring the exciting world of Zig.